So we've depicted here the area under the curve f of x above the x-axis between the points x equals a and x equals b, and we denote it as the definite integral from a to b of f of x dx. Now what I want to do in this video is introduce a third value, c, that is in between a and b. And it could be equal to a or it could be equal to b. So let me just introduce it right just like that. And I could write that a is less than or equal to c, which is less than or equal to b. And what I want to think about is, how does this definite integral relate to the definite integral from a to c and the definite integral from c to b? So let's think through that. So we have the definite integral from a to c of f of x. Actually, I've already used that purple color for the function itself. So let me use green. So we have the integral from a to c of f of x dx, and that, of course, is going to represent this area right over here from a to c under the curve f of x above the x-axis. So that's that. And then we could have the integral from c to b of f of x dx, and that, of course, is going to represent this area right over here. Well, the one thing that probably jumps out at you is that the entire area from a to b, this entire area, is just a sum of these two smaller areas. So this is just equal to that plus that over there. And once again, you might say, why is this integration property useful? That if I found a c that is in this interval, that it's greater than or equal to a and it's less than or equal to b, why is it useful to be able to break up the integral this way? Well, as you'll see, this is really useful. It can be very useful when you're doing when you're looking at functions that have discontinuities. If they have step functions, you can break up the larger integral into smaller integrals. You'll also see that this is useful when we prove the fundamental theorem of calculus. So in general, this is actually a very, very, very useful technique. Let me actually draw an integral where it might be very useful to utilize that property. So if this is a, this is b, and let's say the function, I'm just going to make it constant over an interval. So it's constant from there to there, and then it drops down from there to there. Let's say the function looked like this. Well, you could say that the larger integral, which would be the area under the curve, it would be all of this. Let's just say it's a gap right there, or it jumps down there. So this entire area, you can break up into two smaller areas. So you could break that up into that area right over there, and then this area right over here using this integral property.